The surface area of a sphere. Oddly, the formula for this can be figured out by using the volume formula for a sphere. Consider breaking the sphere into pyramids so that each of the enclosed regions on the surface are the bases of the pyramids. Okay, and that's what this image is going to show us here. What we're doing is taking the surface and break it into a bunch of polygons, which may appear as squares. They could look like trapezoids. They could even be triangles. Just depends on whatever you need. But we break up the surface into a bunch of polygons. We take the vertices of all those polygons and connect them to the center, and you get pyramids. All right, now there's two big points that we need to make about these pyramids. One, the height of the pyramid is going to be the radius of the sphere. Two, the pyramids don't really have flat bases here. However, if we do our best to make as many pyramids as possible, if we aim for an infinite number of pyramids, the curvedness that we have there tends to actually appear flat. And we saw this when we looked at the area formula for a circle. Okay, the more pyramids we get, the skinnier they're going to be, the flatter the base is going to look. Let's recall the volume formula for a pyramid, which is 1/3 the area of the base times the height. For the pyramids that we're looking at here, it's going to look like this. It's going to be 1/3 the area of the base, so whatever that area would be, multiplied by the radius, because the radius is the height of the pyramid. All right, so what I'm going to do is write an expression for the volume of the sphere using the sum of the pyramids. So imagine this broken up into an infinite number of pyramids. Okay, now each pyramid has their own volume. So let's just say we're thinking about our very first pyramid. The volume of that would be 1/3 capital B times R. Okay, and then we have a second pyramid, which is 1/3 capital B times R. However, the bases of the pyramids might not actually be congruent to each other. Okay, they might have different areas. So what we're going to do is add in some subscripts. We're going to call this B1. Let's move that over a sec. Call that B2. And then for our third pyramid, we'll call it B3. Okay, so just to clarify that, these are not all exactly the same thing. They can be different. Okay, and then we'll continue to add them on all the way until you get to, let's just call it Bn. Okay, the aim is for infinity, but we'll just call it Bn. Okay, whatever our last would actually be. Okay, and that represents the volume of the sphere. It's the sum of all of the pyramids put together. So the thing is, we already have a volume formula for the sphere, which is 4/3 pi r cubed. So what I'm going to do is take this volume formula that we know to be true and set it equal to this sum. I seem to have forgotten an R there. Okay, and then what I'm going to do is some factoring, because all of the terms that we have over here have a lot in common. The only thing that's different about them is the base areas that we have here. Okay, so this side, we can factor out a 1/3. We can even factor out the radius length. We can factor out 1/3 R. That will leave behind B1 plus B2 plus B3, all the way to what, again, should be infinity, but I'm going to call just Bn. Okay, and then over here we still got 4/3 pi r cubed. And looking at both sides of the equation, we can simplify a little bit more. We can take out the 1/3 because you also have that 3 on the denominator there. So that leaves you with a 4 and a pi. In addition to that, you can take out the r and drop that down to an r squared. And this will be equal to B1 plus B2 plus B3 plus all the way on. So what's important about this? The area of the first base plus the area of the second base plus the area of the third base plus the area of all the bases that we had built around the sphere. This is the surface area. This is the surface area, which means that the formula for the surface area is 4 pi r squared. All right, example 1, find the surface area of a sphere whose volume is this, which happens to be in terms of pi. Okay, so I'm going to set that equal to the volume formula. We got 12,348 pi, set that equal to 4/3 pi r cubed. Okay, so pi symbols get to cancel. And that's the point of it. That's the point of giving this in terms of pi, so that we can just cancel that out. Okay, now I'm going to take that number multiply by the 3, then divide by the 4, which is going to give me 9,261, which is equal to r cubed. So let's see if that's a perfect cube. And it is. Gives you a radius of 21. And then to calculate the surface area, that'll be 4 pi r squared. So we've got 4 times pi times 21 squared, which in terms of pi will be 1764. Units would be meters squared. And that's an acceptable answer because the problem did begin in terms of pi. However, you can evaluate as a decimal, just multiply by pi. You also get 5,541 point, let's just call it 8. That'll be meters squared. Okay, so both answers are good. The reason this is good is because it starts out in terms of pi.
Later, blah.